Okay, week 9. And actually, with week 9, we start the second part of the course. In the second part, there are 3 lectures left for me to present you. In the first part, we have talked about recurrent neural networks in general and their main applications. In these applications in recurrent neural networks, we had the idea of the recurrence in a network, and we had I have a slide for that. What is we talked about sequence and why sequences needs that feedback, because we talked about that memory. Then we talked about vanilla RNN, what is the problem with the vanilla RNN, how to train RNNs, and trying to train vanilla RNN failing just took us to the idea of LSTMs. And what is that makes LSTM special, we talked about, and you totally understood it because in the exam you were able to answer that question. We talked about how to simply code them. We talked about gated recurrent units, different type of gated recurrent units in addition to LSTM. We talked about modifications on those LSTM units, and we talked about the CNN-RNN marriage and what can it bring and the applications that we've seen in the literature so far. So that was a nice introduction. Actually, if you've checked Coursera or similar platforms for an RNN-related course, most of the courses are based on natural language processing. And I believe natural language processing is a very fundamental field. And actually, it was a very fundamental field before RNNs became a hype, deep learning became a hype. And when I was doing a PhD, I had many friends who were studying that problem. And it is great, important relation to RNNs, because RNNs can modify and manipulate sequence data, pairing bank data, and that's what natural language is. So maybe using these RNNs or natural languages, people have been working on since the last 5-7 years, kind of, and they had fantastic results. So today, we are going to make an introduction to natural language processing with deep learning. But this will be only an introduction, guys. I think there should be a separate course for that. And actually, in many universities there are. In Stanford, there's CS 224. You can find it on YouTube, just like CS 231, the deep learning course, which we have followed in the previous semester's course. And for this one, there's a huge course, NLP with deep learning, CS 224. I strongly recommend that course. I also recommend Tuğba Hoca's course in our department, MMI. Text analytics, it's quite a similar course. You can take it as a special student. So this, subject deserves a complete course. So what can I do in 2 or 3 weeks? Actually, I'm going to spend 2 weeks only to introduce you these concepts, nothing more. Well, I can introduce them to you. That's all I can do. So I'll start by introducing the idea of natural language processing. Well, NLP for short is a subfield of linguistics. Actually, it came from the field of linguistics, which is not an engineering science. It's about literature, guys. And actually, people have been working on linguistics for a long time in history, because language has its own grammar, rules, syntax, and there's a structure for that. If we could understand that structure, we could model it. We could make machines speak. And that was the very main goals of artificial intelligence for the last century, guys. The very first examples of AI in art, in cinema, literature, you can see that the AI speaks, and it speaks very fluently. And we're not there yet. We are trying to get there. We are close to it, but we are close to it for the first time in the history. So that's a very difficult problem. So working natural language processing with machines is machines that understand and just react and provide an answer based on language, guys. So we'll be dealing with that technology. So we'll be introducing ourselves to that technology, and this information I've taken from Wikipedia. So guys, if you ask me what NLP is, there's a nice figure I found on the internet. So it is programming, because you'll need a lot of programming. You need neuroscience, the thing that we do. deep learning, and linguistic. And as it became a part of deep learning, this part became the most important part. We don't care about the linguistics as we did before, because linguistics are the rules, and previously people tried to decode that rule, set of rules. But now we are creating deep learning mechanisms that would make that job for us. So how? To understand that, I'm going to get into the very little history of NLP, because in deep learning or in any science, I told you this before. If you understand the literature, you have to get to the history of it. It is like the literature survey. What we call literature survey in a scientific field is the history of it. Actually, up to 90s, when machine learning became something important and computers became powerful, linguistic was all about symbolic representations. Well, symbolic representations, symbolic NLP or symbolic AI is that representations you maybe know from computational theory. I mean, EE guys will not know it maybe, but I'm sure computer engineering guys are familiar with what I'm saying. There's a subfield of computer engineering which is called computational theory, in which you define grammatical expressions and that kind of stuff, which is related to switching and automata theory, and which you could define in the big picture up to Turing machine. So you can define any set of states or computational operations using these set of expressions, grammar expressions. And it was very, hot topic, starting with the 50s. After Alan Turing came up with this field, it kind of made the field very important. And from that point to 90s, people studied language as if it's a set of rules that we could decode manually as humans by writing some grammatic rules in terms of mathematical expressions. And people have succeeded up to a point, because that approach to the problem was a deterministic approach. We have a set of rules for a language. The language is very huge with some exceptions. Including that exceptions, we can create a model, a mathematical model, which could simulate that rules. So which could simulate that grammatical rules in a mathematical expression. So it was computational linguistics. And they were successful up to a point, but a language is something very dynamic, guys. Every generation speaks another language. You always heard of a grandfather talking about their grandchildren. I just don't understand what they're saying. They're speaking so fast and they're using some words that I don't understand, because the language is dynamic. And approaching the idea of language as a deterministic set of rules is actually the not best way to do it. Because of that, in the 90s, as statistical models of machine learning become very prominent in the literature, there came the age of statistical NLP. Actually, everybody I know from my PhD years who have worked on NLP were statistical NLP guys. They were working on big Bayesian networks where they could model every flow of the language with probabilities, different models, hidden Markov models, Bayesian graphs, or graphical models, etc. And they worked on those models. And statistical NLP was more successful than its predecessor, symbolic NLP. But it had its limits as well, because the language was something very huge, guys. Huge. Language is something huge. There you have thousands of words, and when it comes to sentences, the combination of sentences, they are limitless, and every generation dynamically changes the language and create new set of sentences. So it is probabilistic and it's dynamic. And even though we have seen many improvements in the field during these years, we didn't get an actual Google translator until the 2010s, where we had the neural NLP. I mean, there were studies. I mean, when I was a PhD student, I remember them. They were not mature enough, and those translators, and they were not working correctly. And someday, you remember that day. Someday, everybody was talking about, like 5 years ago, everybody was talking about Google's Translate. That it was working fantastic for the first time, because they switched to a deep learning based NLP architecture. So it is the present now, guys. So what we are going to be talking about in this course, is actually the NLP of the present time. So if you need a literature survey of the symbolic NLP, these are these, and you can use them if you have less data. And actually, people who are working on symbolic AI today are revisiting those studies, because symbolic AI has some advantages compared to deep learning. We have talked about this maybe in the previous videos, I don't remember. So there are literature surveys for that. For statistical NLP, there are more. There's a paper. And starting with the last decade, the state of the art of NLP just moved to deep learning, guys. So we have, and that's what we are going to be talking about. And that's a huge title. That's why I'm going to only introduce you the main concepts, so that if you want, you can continue studying them in your graduate studies. Okay, so why this part of the NLP is close to us? Because they use recurrent neural networks, they use LSTMs, and they use architectures, more complex architectures, which are improvements of LSTMs, like the transformers, which I'm going to introduce most probably next week briefly. Okay, so at this point, I repeat my recommendation. This guy is a very famous guy. He's one of the most known NLP guys in the world. He's a professor in Stanford University, and they have this fantastic course in YouTube. I strongly recommend you watch this course if you're into deep NLP. And they provide every source. I mean, there's just exercises, their slides, and their videos. Actually, I've used a couple of slides, more than a couple of slides of theirs for my presentation, for my slides, for my lecture as well. Okay, so neural NLP is? We simply treat the language as a sequence model. Is it that simple? So you just give the language, you get the language. Well, it is. I mean, there are some versions that you can make it work, but to make it perfect, just like Google Translate does, actually you need to work on the problem a bit more. And there are some parts of the problem which needed more focus compared to the other parts. And actually the most important part was the input, how we input the sequence. And today I'm going to talk about that, the way we input an NLP sequence, a natural language sequence, to an RNN model. Because there's a strong literature for that. And I'm going to introduce that part to you today. Okay? So in order to understand how we input the language, we should speculate on the meaning of a word. Why am I saying this? Because, okay, this is a language. These are some sort of words. You're feeding the words. You're feeding the words to an RNN. So when you do such a thing, RNN is a magical box. It solves many things, but it is best that you understand how that magical box works. Because if you understand how that magical box works, you can design the proper architecture, or you can design the proper representation for that sequence so that the RNN would train itself better. To understand this, we should think about the idea of a word. We are feeding some words and meanings, and that sequential meanings added on top of each other makes the sequence, and you make the sentence which makes up the natural language. Good. So meaning of a word, the meaning of a word, Okay, so how to get the meaning of a word? Today, in the internet, we have fantastic tools. We have very big dictionaries where you can get the meaning. And when you provide a word, you can get the words which are related to them. Because the word's meaning can have multiple meanings. I mean, because some words have two meanings, some words have some broad meanings. So that meaning is represented by that word. And word meanings, I mean, attached to each other, come up with that idea that we want to understand in the natural language processing framework. Good. So what can we do? Basic idea is to use some dictionary. WordNet is a very famous dictionary. Maybe you've seen it on the internet. WordNet is some pristine university's dictionary where you can find synonyms or hypernyms for any word. Synonym is a word, two words having the same meaning. Hypernyms is like the relatives of that word. So I'm going to give you some examples of finding relatives. But so it's not okay. So this WordNet is also a very nice interface because you can interface it with your code as well. It gives you structured code data. You just provide a word. It gives you a structured query of words, related words. So, okay, what is wrong with that? Working with synonyms or hypernyms doesn't help you represent your words because these relations with the words and their word's meaning, the meaning of a word related to another word's meaning on their, I mean, when they're not in a sentence, actually doesn't mean anything to us because you are a good person. Good and proficient are very close words in WordNet. I would never say you're a proficient person. Or if I say that, that most probably doesn't mean that I'm trying to say you're a good person. They're totally different things. So actually, when we say things in natural language, in a language, the meaning of the words are designated within the context of the sentence. So if we are going to define a similarity between the words, which we could use to represent the words, the sequences that we feed to the model mathematically, because it has to be mathematically, because RNNs or other stuff, they're all mathematics, they are just weights. We are going to convert the word to a number in the end, a vector. I don't know how, we are going to talk about this. They should be, I mean, they should have the information of similarity, and that similarity should be related to the context of the sentence. Actually, this is one of the fundamental problems NLP guys try to solve. So this WordNet or any type of dictionary actually doesn't solve the word similarity, as I just put it here. Because word similarity is something context-based. Because any NLP engine you are trying to create actually will be in a context. Imagine we are trying to create a chatbot. A chatbot for Amazon sales website will have a different word meaning similarity matrix in it compared to a chatbot which would be working for a hospital's interface. Because the words you say to somebody who's trying to buy something on the internet and somebody who is having an emergency or ill would have different meanings in sentences, and actually they would come up with different words or sentences. So actually that similarity can only be defined within a context. So actually if we want to understand the meaning of words, because that's how we are going to represent them mathematically later, to feed them to an RNN machine, we have to designate a context and define that relation within that context. And that similarity relation, mathematical relation, should be inside that context, which will be also called corpus, the set of text that you want to understand. Okay, any questions up to now?
I have a question.
Please.
About the last part. Does this mean that we cannot use transfer learning or some kind of something like that that we will see in the next slides, I believe, as effectively as we used in the CNNs?
Well, very good question, Ali. Well, actually, I don't have any slides for transfer learning based or more complicated architectures today. Actually, my last slides a bit are related to that. But the first thing we should say is making transfer learning for RNN architectures or NLP-based architectures are more difficult compared to transfer learning we do in image or sound stuff or in encoders like VGG or other stuff. However, the architectures that we are going to see partially today and next week are not simple architectures. They have different parts and they have encoders and decoders as well. And actually towards the ends of this lecture, the next hour maybe, you are going to see those parts. They could be there will be cases that they could be partially done. For example, let's speculate. I have a model which can translate English to Turkish. Okay. And I know that my model is composed of 3 parts. There's a part that an RNN network, which I call the encoder. I feed the English words. Then there's a second model, which is the intermediate model, maybe which the first part gets the meaning of the English word and feeds it there. And the last part is the decoder, which provides the Turkish language, right? Imagine I want to construct a translator from English to Azerbaijani, which is similar. I would consider using the first encoder part and fine-tune the last part or transfer the last part, maybe. Maybe if your network is, in architecture-wise, complex enough. So that's something we should discuss regarding the architecture. So it is possible, but it is not easy as it is in CNNs or other stuff. Satisfying answer to your question?
Okay, thank you.
Any other questions?